Hello everyone, today's lesson is a combo of 3-1-3-2 in chemical reactions. We call it burning is a chemical reaction. We're going to look at how burning shows a chemical reaction. We're going to start off with this letter from Dr. Young to our student chemists, which are you. She has one more question, so please follow along. Thanks for your explanations. The people of Westfield now understand how the rust in their water could have formed from a chemical reaction between the iron pipes and the fertilizer. However, before the townspeople can consider this mystery solved, they need to be certain that the chemical reaction between the iron pipes and the fertilizer didn't produce any other substances in addition to the rust, which could be dangerous to drink. You've done a good job so far, so I'm assigning this final investigation to you. Review the atomic scale model below, which is actually on the next page, which is similar to the model you created in Chapter 2. This model shows the chemical reaction that formed the rust. If there are any other substances in the water, you should be able to find some clues here. So let's go ahead and review rust molecule models from last time. So we have our iron pipes, which are the Fe atoms, and we combine those with the fertilizer molecule, which is NaNO3. These are considered our reactants in this chemical equation or chemical reaction. The arrow represents a chemical reaction occurring to produce new products, which in this case is rust, and this is the product, but there's a problem. What is missing in the product? We are missing some atoms, aren't we? Because remember what I told you about how all the atoms on this side of the arrow must equal the atoms on this side of the arrow. And so as you can see, we are missing, you guessed it, we're missing an N for nitrogen and Na for sodium on this side. So we know that there's something else. So how did we use scale in this model? How did we use scale? Did we scale up? Or did we scale down? Well, we definitely scaled up because we couldn't see the atoms unless we drew them bigger, right? Okay, so we're going to look at our Chapter 3 question, which is what was produced during the reaction between the iron pipes and the fertilizer. We know that rust was one of those things, but what else was produced? And we're going to investigate that now. So let's look at how paper burns, and this is just a quick little video to show you what paper looks like when it burns. We can definitely tell that there's something new being created here, right? Because it no longer looks white like this side. It has changed, and it is changed into a completely new substance. So we're going to go on to the next page here to choose a claim, and I want you to think about these claims. This is in your packet as well. What happens to the atoms of the substance or a substance when it burns? What happens to those atoms? Either they claim 1, all of the atoms are destroyed. Claim 2, all of the atoms rearranged to form a different substance or different substances. Or claim 3, some of the atoms are destroyed and some of the atoms rearranged to form a different substance or different substances. Okay, so remember, whether the burning substance is paper, methane, ethanol, hydrogen fuel, or another substance, the atoms of a substance are never destroyed. They're never destroyed as the substance burns. They're just rearranged into something else. Okay, so we're going to critique this model here. If you look at the little story or the little scenario, it says Desiree was investigating a chemical reaction. When she heated it up, she found that sulfuric acid, H2SO4, changed into water, H2O. She made the following atomic scale model to show what she thinks happened. So I want you to think about how this is good and how this is bad. So let's look at sulfuric acid, H2SO4. This is our reactant. Then we have our arrow that is yielding water or producing water, which is H2O. This is our product. So what is missing here? What is missing? Well, as you think about the last one we just did, you can see that there are definitely some atoms missing. We only have 3 on this side, and we have 1, 2, 3, 4, 5, 6, 7, right? So we are missing 3 oxygens. We're also missing a sulfur, aren't we? So we can tell that this is definitely not balanced. Okay, the law of conservation of matter, as I've stated before, say that atoms cannot be destroyed or cease to exist during a chemical reaction. This is true for all chemical reactions. All atoms of the reactants must become part of the products. They have to be. It's proven time and time again. Okay, so let's prove that law. Let's look at burning of ethanol at the atomic scale. Okay, so let's prove this law. So we're going to count the atoms on either side of the arrow, and we're going to start with the H's, or the hydrogens. There are 6 there, right? We have 2 carbons, and then we have 6 or 7, that is, oxygens. And then we're going to chemically react them. And as you can see, let's list down what we had. So we had 6 H's, 2 C's, carbons, and 7 O's. Let's make sure the other side has the same amount. So as you can see, we have 1, 2, 3, 4, 5, 6 hydrogens, so that accounts for that, right? We have 1, 2 carbons, so that accounts for that. And let's see if we have 7. 1, 2, 3, 4, 5, 6, and 7. So everything's accounted for, therefore, this is a balanced equation. Okay, so the key concept for today is during a chemical reaction, all the atoms that make up the reactants rearrange to form the products. Remember that. Remember, reactants, arrow, products, and during a chemical reaction, all the atoms that make up the reactants rearrange to form the products. They are not destroyed, they are not created, they just rearrange. So, time to get to work. Today you are doing active reading pages 43 through 46. You can actually listen to it on Amplify, and it'll tell you on the bottom of the page where to find it in the Amplify interface. We're going to do the sim activity. This is a very important part of this lesson today, so make sure you do the pages 47 and 48 following the directions. Then if you want an extra point, you're going to reread on page 49 and answer the 2 questions, and then after your little brain break, you'll take the mastery check on Canvas and then go straight to any should-dos that you need to do. Great job today to you guys. Good luck, and let me know if you need any help.